Welcome all of you once again. In the last class, we started discussing about pulse phase, where we introduced what is a 90-degree pulse, what is the phase of a pulse first of all, what do you mean by a 0-degree pulse, what is a 90-degree phase pulse, what is 180 pulse and 270 pulses. And we also discussed about what happened to the 90-degree pulse, how it tilts the magnetization, the right hand thumb rule, and then after tilting the magnetization by 90-degree pulse, how it rotates. For example, if I apply a 90-degree plus X pulse, what happens? If I apply 90-degree minus X pulse, what happens? And continuously we can apply 90, 180, 270, 360 like that, and make the magnetization to rotate in a direction perpendicular to the axis in which you apply the RF pulse. That is what we discussed. We applied pulse plus X on the plus X axis, and we saw that magnetization rotates in the YZ plane, and depending upon whether you are going to apply along the X axis or minus X axis, this rotation can be either clockwise or anti-clockwise. That was about X axis, rotation about X axis. That is what we discussed. So, we will continue further today and see about what will happen for the rotation about Y axis, and then afterwards subsequently we go to what is a receiver phase, how to understand the receiver phase. So, we will start with what is called the rotation about Y axis today. Now, I am going to apply a 90-degree Y pulse, start with the magnetization which is equilibrium, which is in equilibrium. I apply 90 pulse which is along plus Y. The magnetization, if you apply a right hand thumb rule, if it is like this and then it will tilt back to Z axis, it is like Y axis. Now, the curly fingers tell me the direction of tilting. So, it tilts to plus X axis. So, this is a 90-degree pulse. So, now I continue applying this, increase the length of the pulse in such a way magnetization tilts to 180 degree by minus Z axis. Now, continue and make the magnetization move to 270 degree, it comes to minus X axis, and then finally you apply a 360 degree pulse and bring the magnetization back to Z axis. So, this is what happens. This is a clockwise rotation. Okay. So, it keeps rotating from here. If you see from the center of this, you can see the rotation of the magnetization. So, now you can also apply the same thing around 90 degree minus Y pulse. Instead of along plus axis, you apply along minus Y axis. See what happens, magnetization rotates in the opposite direction. You take it to minus Y, minus X axis, and then continue further, 180 will take it to minus Z, and then further 270 will take it to plus X, and then 360 again bring it back to Z axis. Again one complete rotation of the magnetization you can do. So, what have we understood so far? You can have the amplitude and power of the pulse, width and power of the pulse, you can tune it in such a way. You can apply the pulse either along X axis or minus X axis, plus Y or minus Y axis, and tilt the magnetization to any angle you want. It need not be 90, 180, it can be any in between also. So, finally, you can make the magnetization to rotate in a direction in which you are applying the RF pulse. You can make it rotate clockwise or you can make it rotate anti-clockwise, both are possible. So, this is where the phases of the pulses are very, very important, and with this you can control the behavior of the spins. You can tune the magnetization and design the pulses in such a way you can do whatever you want, and make sure that the spins align rotate in a particular direction and a particular plane, so that you can get the information, retrieve the information from the spectrum the way you want by designing the pulses. So, pulse space is very, very important. So, now this is a clockwise rotation of the YZ plane. Now, completely we understood what is rotation about X axis, about Y axis when you apply RF pulses, and how the magnetization rotates. Now, I am going to introduce another thing called a receiver phase. Okay, you are applying the pulses along X or Y axis, that is a pulse phase. You can also apply receiver phase. You can also have the receiver phase, not apply, you can see when they receive the signal how you receive. For example, receiver is usually kept at an axis to detect a signal. Of course, that should be possible. Even in the first class we told you, a magnetization is along Z axis, you apply a pulse along X axis, you will have a receiver along Y axis to detect. So, they are all orthogonal to each other, all the three. The direction of application of the pulse, thermal equilibrium magnetization, and the detection, the receiver area you are going to keep, all the three are orthogonal to each other. The way you tilt it depends upon where you apply pulse, that is okay. So, that means usually receiver is kept on axis in the transverse plane, and this axis is called a reference axis. That is important thing. So, the magnetization aligned at the reference axis gives a absorption mode signal. Very important point. If I have a receiver in the axis where magnetization is aligned, then I am going to get absorption mode signal. If the magnetization differs by 90 degrees from this, we are going to get a dispersion mode signal. This is a concept which is always we use very often now, absorption mode signal, dispersion mode signal, etc. in understanding phase cycling. So, what is that absorption mode signal? What is the dispersive mode signal? See, this is the absorption mode signal where you can see the signal positive and it is completely absorbed. This is center, this is gives the frequency of it, and this is in general called an absorption mode signal. Same thing if it is a 90 degree out of phase, this is the dispersion mode signal, it will be like this. Again at the center of this is where you can measure the frequency. Absorption and dispersion are just out of phase by 90 degrees. Of course, when you were understanding the Fourier transformation, we knew that this is a cosine part of the signal, this is the sine part of the signal, we knew that. But anyway, I did not introduce that, but I am just telling you what is an absorption mode signal and what is a dispersion mode signal. You may ask me a question, what happens if I apply the magnetization at any other angle? At any other angle, instead of being at x axis or y axis, I have a receiver, magnetization I will tilt to in between, let us say x and z axis, somewhere at 45 degrees. What is the type of signal I get? It is neither absorption nor dispersion, it is a mixture phase. It has both absorption and dispersion character. The resonances, if I apply a pulse, I have a, let us say this is my receiver phase, I have kept a receiver here, and instead of tilting here, exactly if I tilt here, I am going to get absorption mode signal, and the magnetization here will be dispersive mode. If I have a signal here somewhere in between, then you have component of the cosine component and the sine component, both you will be present, and that means as a consequence of that, they are not exactly out of phase by 90 degree, the mixture phase will be present. Okay. So, another thing which we also discussed in the Fourier transformation, we knew the Fourier transformation of a real function and imaginary component both. When you do a signal, I take a signal like cosine, sine or cosine, or for example Gaussian or Lorentzian, any function you take. When we understood the mathematics of the Fourier transformation, we knew that Fourier transformation of any function like that always results in real component and imaginary components of this. They differ by 90 degree. This is important point. And the real part is what is called absorption. That is what I said in the previous slide. When I see a signal like this, which is absorption, when I see a signal like this, it is dispersive. This is absorption signal is the real part of it, and dispersive is the imaginary part of it. Or in other words, this is the cosine part and this is sine part of the Fourier transform signal. So, now let us understand bit more. I will bring the magnetization to x axis by applying 90 degree pulse. I will put my detector along x axis. This is what it is. I bring the magnetization from thermal equilibrium to x axis. It is my detector. I am detecting here. This is my receiver. Detector means receiver I am telling. I am receiving the signal here. What is happening here? My receiver is here. Magnetization is also along the same axis. What I should get? I told you, you must get an absorptive mode signal. This is the absorptive mode signal. Because the Fourier transformation has a real and imaginary part, now the real part is absorptive, this is here. And imaginary part, there is a out of phase penalty, there is a signal here. You have two receivers to receive. One receiver receives this, other receiver receives this signal. Then what will happen? That will be signal along my, mx and my components will be there, magnetization component. Mx component you will detect as a pure absorptive mode, and whereas my component will be imaginary part. It will be out of phase by 90 degree. It is a dispersive component. So, that is what simple, you apply 90 degree pulse, bring the magnetization to x axis, my detector is along x axis, absorption is real and dispersive is imaginary, and then what mx component is absorptive and my component which is imaginary. So, the real part of the spectrum is always for the cosine and imaginary part is always dispersion part is sine component. Now, what I will do is after bringing the magnetization here, I will allow it to rotate by 180 degree. Then what will happen? The signal will start coming here, magnetization moves here, from plus axis it moves to minus x axis. Then what is going to happen? If I detect the signal when they move by 180 degree, the real part will become negative absorption, whereas dispersive part also becomes negative dispersion. Again it is also out of phase by 90 degree. So, what is going to happen? The real part will be negative absorption and imaginary part is negative dispersion when I allow the magnetization to rotate by 180 degree. Now, what I am going to do is, this is what the signal what we observed, this is the negative absorption, this is imaginary part. Now, I have moved the magnetization from this to this either way, in whether you move clockwise or anti-clockwise does not matter, it is rotating. Now, once mx signal is here and now I am detecting signal here. So, what you are going to get is negative dispersion. In fact, mx I should put here because it is already moved here. Okay. So, the phase shift is 180 degree. So, real part is negative absorption and imaginary part is negative dispersion. Fine. Now, I am going to apply a x pulse and rotate the magnetization to y axis. Detector is along x axis. Okay, this is what we are going to get. Now, remember I am applying x pulse, magnetization is along my axis, but my detector is still here, receiver I have not changed. So, what is going to happen? There is a phase shift already by 90 degree. So, what does it mean? The real part now becomes like a dispersive signal and imaginary part becomes absorptive signal. It looks like absorptive because there is both of them are changing in the phase by 90 degree, because I have not changed the position of my receiver. My receiver is here only, but the magnetization out of phase by 90 degree. So, the real component of it is dispersive, looks like dispersive, whereas imaginary part looks like absorptive. So, this is the important point when you apply a pulse on an x axis and still your receiver is not changed. So, what do you understand from this? You can apply pulses in any axis and you can also change the axis of the receiver. Receiver need not be here. On the other hand, if I move the receiver here, what would have happened? Still you would have got the absorptive signal in the real part and dispersive in the imaginary if the receiver has moved here. While I move the magnetization by 90 degree, I can also move the receiver in the same direction. Along with the my, I will also move by 90 degree. Then you are going to get absorptive and this will be real, this will be imaginary. But right now our magnetization is here and our detector is here. This is what the signal. Now, allow the magnetization rotate by any angle phi, as I told you, it is somewhere here. What is the type of signal you are going to get? Now, you have mx component, also my component, both are present here, mx and my both are present. So, it is a mixture of absorptive and dispersive. See here, it is not absorptive, there is a phase error here. Phase is, if it is a really phase signal, there should not be any phase error, it should be like this. If there is a phase error, it will be like this signal. So, there is a mixture of phase here. It is not pure absorptive nor pure dispersive. Similarly, in the imaginary part also there is a phase distortion. This is a mixture phase. So, this is what happens when you apply a pulse at any other angle other than the 90 degree, you will have a mixture of components from real and imaginary. The phase is not pure phase, it is mixture phase. Okay. So, now you may ask me a question, I need to detect both the signals. How do we do that? Of course, in NMR that is what is done. We detect the both real and imaginary part of the signal. That means we have two receivers that are kept in opposite phases by 90 degree that we require. This is called quadrature detection. I told in our earlier course what is the quadrature detection. I have two receivers kept exact out of phase by 90 degree. One receiver R1 here, other is R2 here, receiver 1 and receiver 2. Then here I will receive real part, in this receiver I will receive imaginary part of the signal, both I can detect. Okay, that is two receivers are required. So, in quadrature detection generally we do, and they should be exactly out of phase by 90 degree. Otherwise, there will be phase error and we need to correct the phase. And remember, how do we correct the phase? We discussed this when we discussed the Fourier transformation. Now, I will introduce something about Fourier transformation of a cosine and sine function, because we require this for understanding the phase cycling. You know what is a cosine function? Cosine function is very simple. The detected signal mx with the receiver is also along x axis is a cosine signal, and you start like this. It is like this. Start with x at 0, it is maximum value is 1, and it oscillates. It is a oscillatory function. Okay, this is cosine function. Now I do the Fourier transformation of this. I get two frequencies, real and imaginary, which are plus omega and minus omega. This is the Fourier transformation of the cosine function. Gives negative and positive frequency. Why negative and positive frequency? Because cosine is an even function. Now if you detect My magnetization, it is a sine signal. Of course, this is the Mx magnetization, magnetization I am talking. We get two signal. Now if My magnetization, if I detect, that is the sine part, or of course this itself, cosine signal itself, if you do this thing, then Fourier transformation of this you get minus omega and plus omega, they are out of phase by 90 degree. One is negative absorption, other is positive absorption. See, if you detect the Mx part of the signal and do the Fourier transformation of it, you get two frequencies, minus omega and plus omega, because the cosine is a even function. If you detect this My component of it, that is a sine component, when you do the Fourier transformation, you get again two frequencies, minus omega and plus omega. Omega is a frequency, but one is negative omega is negative absorption peak, positive omega is positive absorption peak. This is what you are going to get, the Fourier transformation of a cosine sine function. This is the Fourier transformation of a cosine function. Now I will do one trick. I will do the Fourier transformation of both these functions individually. This is the FT of a cosine function, that is what we discussed. We have negative and positive absorption. I will take the FT of a cosine function, I have negative and positive, both are there. Let us add up both of them. What will happen? If I add both the Fourier transformation together, Fourier transformation linear function, I told you we can also add it up in the time domain or the frequency domain. You add up both of them, then what will happen? This will cancel out, positive and negative signal, and you are going to get only one signal which is along, which is at plus omega. This is what we do. We can do very often. I can eliminate one of the component, imaginary component now. Sine component I removed, or negative component I removed. I get only positive signal by co-addition of the Fourier transformation of a cosine function and the sine function. Now you may ask me a question, hey, what is going to happen if the cancellation is not perfect? That is what I told you. The real and imaginary part, the detectors should be exactly out of phase by 90 degree. In the electronics, the equipment, the gain should be equal. If there is a gain is not same, or exactly they are not out of phase by 90 degree, there will be a phase error. Even though you have a detector at exactly two places like this, let us say the phase difference is not 90, it is about 88, you get into phase errors. Now this happens for unequal gain or amplification, negative and positive peaks are not of equal intensity. Then what will happen? There is no cancellation at all. Cancellation is not efficient. I do the Fourier transformation of the Mx component, get negative omega and positive omega. I take the Fourier transformation of the My component, take negative omega and positive omega. Negative omega here is negative dispersion, I will coordinate, but instead of cancellation there will be some portion of the signal left there. It is not going to completely cancel out. Then what will happen? It gives rise to problems. What do you do in such a situation? This is where receiver phase, pulse phase understand is very, very important. We can do some trick to cancel it. Let us assume the imaginary part has a gain of 10% more than the real channel, real signal. You see, I will do the Fourier transformation. The real part is, let us say cosine part, is 10% more than the sine part. So cancellation is not possible here 100%. Now we see a signal Mx equal to sine some frequency, and signal for My equal to cosine of 2 pi nu into t. True, because what is going to happen is this is not 100% equal. So this is 2 pi nu t, this is 1.1 times, because 10% more I have taken as the gain. Imaginary part is 10% more. Okay. So now we carry out 4 acquisition, 4 times experimental do. Acquisition means I will acquire the signal 4 times, and each time I do a trick. I will change the pulse phase. First time I will do an experiment, collect the signal, first experiment. I put my pulse phase along plus x, that is I put the RF pulse along plus x axis. Then magnetization, as you know, when I apply a 90-degree pulse, does not matter whatever is the gain, I phase difference between two receivers, my pulse is along x axis is 90-degree pulse. It has to bring the magnetization to minus y, that I know. It will bring the magnetization to minus y. Now mx component will be sine of this and my component is 1 minus 1 cosine of this one. That is correct, because we have seen that. Now I will do another experiment. I will put the pulse along plus y. Then magnetization comes along plus x, and then again this will be cosine part will be mx and sine part will be 1.1 times my. It is simple, that is what we understood so far. When you apply RF pulses at different axes, where does the magnetization come, and if you have a receiver at different axis, how we get the mx and my component we discussed. We now do a third experiment, mx apply a pulse RF pulse along minus x. The pulse phase is minus x and receiver place is plus y. Then this is what the signal you are going to get for mx and my. Do a fourth experiment at minus y, signal starts at minus x, and do the you are going to get the mx as cosine part and my as the sine part, like this. Fine. See, somehow the 10% gain of the imaginary part is like this. Because I am changing the receiver every time at different places. Now you see, once it is minus 1.1 times cosine of this, once 1.1 times sine, 1.1 times cosine, 1.1 minus 1.1 of 1 times of the sine function. What is the FID of the real part? Is the mx of 1, this is 1, m plus my of 2, this one, minus mx of 3 and minus mi of 4. All the 4, it is nothing but the FID for the real part. I add up all these things. Then I am going to get 4.2 times sine of 2 pi nu t. So in another case what I will do, I will take the FID of the imaginary part, that is this is whatever you took mx, you have to take my for this now, in real part, imaginary part. My equal to mi of 1 you take, and mx of 2, mi of 3 and mx of 4 you take. And now co-add everything, it turns out to be minus 4.2 cosine of 2 pi nu t. What did you do? Now although gains are phase exactly, these two receivers may not be exactly out of phase by 90 degree, but you have done this phasing of the pulses and the receiver in such a way, you change the position of the pulses and also the receiver. When you do 4 different experiments and co-add the signal, this is also plus 4.2 times, this is minus 4.2 times. Now what you have done? The two FIDs are perfectly balanced. Two parts of the FID, the real part and the imaginary part are perfectly balanced. Does not matter whether the two receivers are matching or not, the gain may be different. But as far as we are concerned, when we start collecting the signal, we have managed to such a way that both real part of the signal and imaginary part of the signal get completely balanced. Now what will happen? What did we achieve? This is what is called elimination of the artifacts, instrumental artifact. This is an instrumental artifact because the gain is not exactly same. By doing this type of an experiment, by co-adding the signal, we have removed the artifact which comes because of imbalance in the receiver gains, which is not balanced. What do you call this technique? This technique is called phase cycling. Phase cycling is a method in NMR where you can cycle the phase of the receiver or you can cycle the phase of the pulses. Either of them you can do. Design the way you want to see that only you can all this type of artifacts can be eliminated. Not only for this, you can also do this type of phase cycling to get particular information you want. I can get a particular signal. When we talk about coherent selection, everything, I will discuss these things. So this way, the phase cycling component is very, very important in NMR. That is what I wanted to tell you. Receiver phase and the pulse phase must be very clear in your mind, depending upon where I apply the pulse, where I apply the receiver, whether the detected signal is real or imaginary. whether it is absorptive or dispersive or it is a mixture, everything we know, and based on that we can manipulate in such a way we can get the signal without any errors, without any phase artifacts, because because of the instrument or because of any collection of the signal due to different phase distortion. So, all these things we can do, this is called phase cycling. Okay. So, with this what I am going to, what I wanted to tell you is about the receiver phase and the pulse phase. So, today in the last class and this class what we understood is how we can deal with the phases of the pulses, what is a pulse phase, how do you tilt the magnetization of different axes, what is do not ever to get confused at all, simply remember pulse phase is the phase of the pulse in which axis you are applying. If you apply a pulse along the x axis, it is 90, if it is a 90 pulse, it is a 90 x pulse. If you are applying along y axis, it is a 90 pulse means 90 y axis, or 90 minus x, 90 minus, this is the pulse phase. Similarly, the receiver phase, where you keep the receiver that is the x axis or y axis or minus x or plus minus y. Accordingly, the detected signal is either absorptive component or dispersive component. Sometimes it is depending upon whether the receiver is here, magnetization, receiver is along x axis, magnetization is along y axis, what are you going to get? You will get real part dispersive and imaginary part absorptive. So, this is what happens. So, all these things if you understand, we can start playing with these pulse sequences, playing these pulse phases and receiver phases and design the pulse sequence of our choice to get the orchestrated way we can get the information we want from the NMR spectrum. So, this is what I wanted to tell you about this today. So, now time is almost coming to an end, I am going to stop now. In the next class we will talk about evolution of chemical shifts and evolution of the J coupling in different pulse sequences. Okay. There I am going to introduce this now I introduced absorptive and dispersive components. There I am going to introduce in phase and anti-phase signal. How do you understand those things and how the magnetization evolves, how the chemical shifts evolves, how the coupling evolves when we acquire the signal in different pulses. So, this we will discuss in the next class. I am going to stop here. Thank you.